So the next speaker is Professor Mariano Martinez, coming from Universidad de Salamanca in Spain. Basically, he graduated there as a chemical engineer and also the PhD, and then moved to Carnegie Mellon for a postdoc in process systems engineering, and also has industrial experience in G. He has also received several awards, including the Fulbright Scholarship, the top doctoral student in Salamanca, and actually is working in applying process optimization to a range of problems. And today we'll be talking about simultaneous optimization of the design of the product, process, and supply chain for formulated products. Thank you for coming.
Thank you very much, Gonzalo, for the kind introduction, and thank you, Professors Gani and Chen, for giving me the opportunity to bring my group's work here. A few years ago, the second workshop, Professor Gani asked us, what are you going to present in the next one? So what I'm trying to, what I bring here is basically the answer to that question. Basically, we can talk about two different kind of products. The one that is made from mixing a number of ingredients, that's basically what you have anytime you buy shampoo, a perfume, or something like that. There are cosmetics. Or thinking reversely, you have biomass, you have crude, which is made of a number of ingredients. In the end, we are going to separate them to get final products. So basically, we are going to be presenting three cases, three examples, for these different formulated products. The first one, the formulated product is biomass. We are going to see how can we design the biomass depending on the final products or even the cost of the market of those products. The second example is a little bit more related to energy. Is the selection of a heat transfer fluid for the operation of organic ranking cycle. And the third one is a formulated product made by mixing a number of ingredients. And it is where the supply chain is going to be considered. The third example actually is related to a biorefinery. The idea is biomasses are made of a number of ingredients like cellulose, semicellulose, lignin. If we talk about algae, we have lipids, we have carbohydrates, and so on. We are going to separate them. And the idea is, for this particular case, we have two different products, xylitol and sorbitol. The price in the market is different. So, while xylitol comes from C5 sugars, sorbitol comes from C6 sugars. So, on the one hand, we have to select the technologies to process the biomass, pretreatment, fermentation, or catalysis for the synthesis and purification. And on the other hand, we can play with the biomass or with the composition of the biomass. I'm not going to go into the details because of the time, but we have the models. We have to model all the units of that process, all the alternatives. We use first principles, mass energy balances, thermochemical equilibrium, phase equilibrium, kinetics if we need it. Here you have a little bit of the thermodynamics for the crystallization. So the idea is that first, process design, we are going to select the technologies, and for that is basically solving this superstructure, and we see that dilute acid followed by catalytic hydrogenation is the best one. But the thing is that you have a number of biomasses available, waste biomasses. You have residues from the forest, residues from harvesting, and so on. The first problem can be minimize the production cost of that facility. For that, depending on the initial biomass, depending on the raw material and so on, you find different costs. The best one turned out to be corn stock. We can think of the problem differently. Because of the different price of xylitol and sorbitol, we can have a biomass that we engineer for the composition. So xylitol is more expensive than sorbitol. If we optimize the profit, we get a biomass that requires around 40% hemicellulose. That biomass, the closest that we can find is something like the sargassum algae. And you see that the production cost is closer to switchgrass, but it's a little higher than the corn stock. So basically, that biomass maybe cannot be produced. That's why we try to find something that is available in the nature, but otherwise we can try to engineer one which 40% cellulose, any cellulose, 20% cellulose. Another example is related to the selection of heat transfer fluid. Basically here, the problem that we have is these fluids are toxic and flammable, and also depending on the thermodynamics, they generate more or less power. So we develop or propose a two-step methodology. The first one, basically because of the number of heat exchanger fluids that can be used, it's kind of a pre-screening. The pre-screening will somehow reduce the number of alternatives in terms of fluids and in terms of cycles. The cycles depend on the layout and the type. We will see the example later. And also, we can select the type of facility depending on the availability of the resource. The first one, the first stage is the pre-screening, and try to use a simple flow sheet, consider risk assessment and environmental impact to screen the possible fluids, and with that we go for a more detailed optimization, considering again environmental safety and economics in order to select the layout, the type of fluid, and the operating condition of all the units. The first stage uses a very simple flow sheet, but again considers the three terms in the objective function. Basically, we come up with a few organics there, toluene, benzene, cyclohexane. And in the second one, we also pre-select two different cycles, organic rankine cycle and organic flash. And within each one, there are several configurations that we have to select. But we have to include the thermodynamics, the proper thermodynamics of the fluid. And for that we use Alamo in this case to obtain correlations for the enthalpy and entropy for each one of the fluids. As I mentioned before, each one of the Rankine cycles have a different structure. So in the case of the organic Rankine cycle, we consider the possibility of two pressure levels. Can be only one, but it's a part of the optimization to be selected. And of course, the operating conditions, pressures and temperatures across the flow sheet. The second one is the organic flash Rankine cycle. We have two different ones, and it can be used only one, but that's from the optimization to decide. So we apply it first, of course, for the geothermal, but it can be also applied to any hot waste residue, liquid and gas. And actually, the difference in cost and prices depends basically on the area of the heat exchangers. If you work with gases, the heat transfer is poor, and as a result, the areas are higher and more expensive, the heat exchangers. So one of the things that affects, in the case of the geothermal also, is related to the temperature of the source, and how that affects the selection of the fluid and the selection of the cycle. Here you see some of the figures, basically because we are going to be using these figures to select which is the kind of facility depending on the depth and the temperature of the resource. So basically you see that in places, I'm coming from here, Salamanca, this is Madrid, Barcelona, basically probably you know more these other two cities, and you see that depending on the temperature and the type of the residue, and the resource, you see in this case in Madrid, basically you are targeting an organic flash Rankine cycle because of the 140 degrees C, and if you go, for instance, to another temperature, 110, here close to Barcelona, for instance, you go to the other configuration. And each configuration selects the proper fluid. And then the final example, I think I more or less go the time because this is the longest one, that's why. So basically, we are going to be integrating all the way from process to supply chain. Basically, what happens with blending? Blending means that we are going to take ingredients that are made from different companies at different places. We are going to mix them. They have to be processed. So we have engineering constraints for that. And basically this is the kind of problem. On the one hand, we have to, or we can design the ingredient. That's part of the work that Professor Kani has been doing for years also. Once we have the ingredients, we are going to mix them. That's the kind of plan. We are going to present the example of a detergent, basically because it's the one we've been working on. This is the dry prime. Sorry. Mixing is basically a pooling problem. So basically, we're going to be in the core of the problem is going to be an extended pooling problem to consider the mixing and process constraints and so on. But we have to integrate that pooling problem within a supply chain, because in the end you are going to buy those ingredients from different companies producing them. So let's start just with this particular case. First, we are going to look for ingredients that have the proper properties for our final product. How can we do this? Actually, this is, on the one hand, this is a molecular design problem. This is combining molecular design with the synthesis. First, we have to select which is the molecule. This is the work that is currently being done by one of my PhD students. We are going to design the head of the tail and impose the conditions for the surfactant. We need, of course, the prediction model for the behavior, for the properties of that surfactant. Once we come up with that, we have to synthesize, and we are looking also for surfactants that are biodegradable, or that come from ingredients other than crude oil. So in this case, we are going to target APG. Actually, was one of the ones selected. APG is a surfactant that can be produced from algae, but we want to develop a process that is somehow integrated, in the sense that we can produce all the ingredients, the tail and the head of the surfactant from renewable resources. Actually, in order to do that, this is the head comes basically from sugars, the tail from oil. We can do that from the algae. Again, a product design problem. In this case, the product to be designed is the algae, the composition of the algae for that. And this is the process that allows us to do that. We have digestion of waste. The digestion generates biogas. The biogas is going to be used to produce hydrogen. On the other hand, the digestion also produces nutrients. The nutrients are going to be used to grow the algae together with CO2. With that, we separate the lipids and the carbohydrates. The lipids are going to be hydrogenated to produce the alcohol that is needed. On the other hand, we have the carbohydrates, the sugars. We are going to break down the sugars to produce glucose and fructose, and the sugar plus the alcohol, we get the APG. So we've designed the molecule. Now we evaluate the production. We have a new molecule that is possible to be synthesized and to be produced from a sustainable resource. This is our molecule. This is the algae design problem. An algae that is basically we target 60% lipid, 27% carbohydrates for our APG product to be produced out of that thing. And for it to be competitive, basically the market price is there. So actually here, basically what we are trying to do is to evaluate how much waste we need to collect in order for this production process to be competitive with the current production of this. This is just basically where how much of the waste has to be collected. Basically, in most of the provinces in Spain with a large or medium cattle community, we can obtain that. Once we have the ingredients, that was just one example to get one of the ingredients. Of course, apart from surfactant, you have also antifoam, you have enzymes and so on. You are going to formulate the pooling problem. Before the pooling problem, the pooling problem is also related to how we are going to process that mixture. That mixture has to be dry, and one of the big issues is designing this apparatus. Actually, this is a spray dryer. I have a couple of very good friends working here in China, in P&G China, Beijing. They were both postdocs with me at Newcastle, and actually they were also working on that dryer. So basically the problem here is you have to produce the particle that is from 0.4 to 0.5 millimeters, because that's the proper size for your detergent the moment you take a piece. So basically that's obtained because of the ingredients. The ingredients affect the particle size and also the properties, the drying, the operating conditions for that particle to grow. With that, we obtain basically process constraints for our polling problem. Okay, so that particle size that I mentioned before comes from the study of this unit. The pooling problem actually is something that most of you are familiar with. The only thing here is that we have to also consider product properties or policy properties for the cost. If you buy a large amount, you get a discount. There are different laws for that. You have the process constraints also related to the drying state before. You have the detergent performance, basically how your mixture is going to clean your clothes, for instance, and also lately it's very important to include the environmental burden of your detergent. That's the reason why we also were producing ingredients that were more sustainable than the ones coming from crude, or at least biodegradable compared to the ones coming from crude. So we formulate this problem, but on top of that problem, or using that pooling problem as the core, we consider also the suppliers, the different companies that actually are producing the surfactants, the antifoam, etc., and the consumers. This is a very large MI-NLP problem. If it's a regular pooling problem, you target global optimization. We didn't do that, it was too large for us. But even to solve it, if you apply to an industrial relevant size problem, is difficult. Actually, the example we were targeting was Europe, and you will see more than 3 billion equations. And for that, we developed an algorithm, a decomposition algorithm, basically similar to outer approximation. The only thing is we were kind of targeting which kind of approximations were done. One of the good things here is because we know the product, we know the ingredients, we were evaluating also which are the composition for that. This is basically the algorithm. It has 2 parts. We are going to initialize each one of the possible locations of the facilities that allow us to create those converse codes for the optimization, and we later run the typical MILP and NLP decomposition for the solution of our problem. This is not this is a case study with real surfactants, real builders and bleaches, but that's not the one the company is solving. But it's basically the size of the problem is similar. We use 14 different ingredients, 2 surfactants, 2 builders, bleaches, and we consider 3 different final products. One which is the best brand that they produce, one which is medium, which is a little lower, to see where we are going to be producing each one of that. And we target the entire Western Europe. Basically, the customers are the big supermarkets. That's what the typical one is Sainsbury's and Tesco in the UK, Carrefour in France, Mercadona in Spain, something like that. So they are actual real ones. We have real suppliers for the organic suppliers, enzymatic enzyme suppliers and inorganic across Europe, BSF, Monsanto, the location of those facilities, and we pre-selected 68 possible locations for our facilities to be located. Those blue points that you can see around the map. We optimize the full thing using the composition algorithm I presented in the previous slide, and we see basically three regions of influence: a central region in Europe that is covered by that facility. Actually, that is located in France, and is targeting all the facilities produce the three products. The only difference is that depending on the market around the area, it's going to target or focus more on the production of one of the three. Another one will be located in southern Europe for the region Italy, south of France, Spain, Portugal, and so on. And the third one is targeting the Eastern European part, like Poland, Czech Republic, Hungary, and so on. And basically, apart from the location, we also get the composition of the detergents. Basically, each detergent, you will see that detergent 1, 2, and 3, even though it's supposed to be the same, what we have is a range of composition for each one of them. In most of the cases, is similar. One is similar in most of the cases, but there are some small differences in some of the ingredients. So with this, basically, have more or less good timing. Actually, we've been presenting three different cases of example for formulated products. Formulated product is not only the product that you sell. Formulated product can also be the ingredient or the raw material. In terms of raw material, we're talking about biomass. Two cases, the lignocellulosic, but also the algae, as part of the last example. In terms of the refinery problems, how we can, on the one hand, design the raw material or select the raw material, actually that includes modeling the entire flow sheet. You see that we have to consider all the operations to determine which is the composition of our raw material for the final product to be better produced. Another different area is related to the heat transfer fluid. This is particularly important to consider the thermodynamics, because actually it's the one that determines the power that is going to get out of the flow sheet. As a result, involves developing proper correlations for the thermodynamic properties to be embedded in the optimization. And the last example basically is anything related to the consumer product that we have all the day, and even though the core is an extended cooling problem, we have to add process, we have to add supply, and that complicates the problem. The problem is relatively big. I mentioned 3 million equations, 1.5 million continuous variables. I don't remember, I think it's 50 or 70,000 binaries, and so on. So we have to develop tailor-made algorithms. We haven't tried like machine learning to try to solve that. That could be an interesting challenge to do that. But again, commercial solvers cannot handle the problem as such, at least an industrial size relevant problem. So with this, of course, thank the funding for all this. And just to mention a little bit the group, the ones working right now on the topic is the ones with the blue square. But also I'd like to thank the previous ones who started. Borja was also a postdoc with Mariano a few years ago. Was the one working a lot on the product design related to the spray dryer, the modeling with CFD, and so on. And Manuel was responsible for the supply chain and integrating the supply chain and pulling problem. So with this, I'd like to thank you all for your attention, and we will be happy to take the questions after the photo, after the next session. Thank you very much.